All right, it's 1:50, so we'll go ahead and begin. Hope you guys had a nice fall break and everything. We have some midterm exam results that I feel like we should spend a bit of time talking about. I'm also planning on maybe making up a form just to kind of gather some more feedback about the midterm. As you can tell from exam one, or test one, the online test, right? These numbers seem lower. And typically when we display, averages and whatnot to students, it's good to maybe break this down based on how much web work folks are doing. And so you can notice here that for students who are doing less than 50% of the web work, right, that average is dreadful, right? Less than 40% on the exam, but I guess if you're only doing 50% of the homework, 40% on the exam is maybe reasonable or to be expected. What's maybe a little bit sadder and is down here near the bottom, right? Those who are doing 90 to 100% are averaging close to a 70%, but not quite, right? And we don't have all the scores in or anything like this yet, but did just want to get these out. But the TAs are still grading and should be done by tonight. So two things, I guess, regarding this. The first is, while this is low, it's not entirely unexpected, sadly. If you look back on previous semesters on the, what was then, like a test two or whatnot before we called this thing a midterm or what have you, that the average is pretty consistent with what we see here. But that being said, there's something funny because, this was an in-person one. And I know that they originally had wanted to not have the midterm be included on the drop, but right, because this is quite low, it kind of makes more sense for this to be included on the drop than not to be, right? And so that's why the change in policy here was to revert this back to now that you can actually drop your midterm exam rather than dropping one of the online tests, right? So if you still do quite well on those, you can drop the midterm and replace it with your final exam score. So I thought that was a net positive overall. The other kind of big point that I want to bring up is that, so tomorrow in recitation, you're going to be getting back your midterms, right? So you get to keep these things, you get to study off of them and prepare for the final exam and all that sort of stuff. I would recommend that when you go and so they're going to do some of the commonly missed problems and then also give you a chance to come up maybe near the end and ask if you have any grading questions and things like that. Certainly take notes while they are going over some of these most commonly missed problems, especially if it's one that you missed, either on a separate piece of paper, right? Or use like a colored pen or pencil or something like this that you didn't use to write on the exam. Of course, if you start marking on your exam and you find out that there was a grading mistake, right? That you think that you should have gotten more points back than you were actually given, right? If you've marked on it with pencil, they can't give you points back, right? And so that's why I recommend to actually write on another piece of paper, excuse me, or to use like a colored pen or something like this. So that way there's no confusion about what you did while you were on the exam versus what you're just taking notes of for studying for the final. I think that's the majority of my admin stuff. What was the toughest question on the exam for you? Yeah?
Like the constant to the power of a variable, and
okay.
I haven't seen one of those like two.
Okay. So yeah, so an integral of like 2 to the x or something like this. Okay. Any other ones? Yeah.
So line integrals talking about conservative, not conservative, like a half circle.
Oh, I think I remember there was like a true false, right? Some true false question. Okay. Any others that you'd like to kick up to the top of the list? What do you think was most difficult? Okay. Well, like I said, I think I want to make a form or something just to kind of get some more feedback about the midterm exam and just kind of overall perspectives and whatnot of that. So I'll probably get that posted to D2L or maybe just Piazza or something like this, maybe later today or tomorrow. So I'll be on the lookout for that just because I am interested in getting kind of feedback. Like I said, we did look at previous semesters. I think Last semester, I think you guys, the average is like a little bit better, but the semester before, your average is a little bit lower. So you're kind of like in the middle. Again, not to be, this isn't unexpected, but still, I of course would have liked to see this even higher. I think many of you can agree with that, right? All right. Well, we do have math to cover today. I guess the other big thing is that that I mentioned here is just don't get discouraged. There's lots of time to improve your grade between now and then. So if you did get a lower score than you were hoping for, right, there are still lots of points out there, including the final exam, which now can replace the midterm. And so the biggest thing is, right, don't get discouraged. Try to, put in a bit more effort if you can, if you have the time or whatnot. Meet with me during office hours, that sort of thing. But yeah, give it all your all. All right. I guess any other admin questions before we transition to our math for today? Yeah. So yeah, the question is for our next test, the second online test is, yes, it's largely over chapter 15. I think there's also 16.5, which is basically a lot of this is revisiting the fundamental theorem of line integrals. So, but yeah, lots of integrals, doubles and triples. All right, well, let's go ahead then and transition. And today we're talking about 15.2. And there was no pre-class video for this one. There is a pre-class video for Friday's stuff about integrals over general regions, so 15.3. But today's class, we should be able to make the majority of the way through it. So as I mentioned in our class last Friday, 15.1 and whatnot, that when in Calculus 1, we had a section very similar to what we had here in 15.1, where we had Riemann sums and limits of Riemann sums. And they were a pain back in Calculus 1, and they were even more of a pain. You can probably, with those limits and those double integrals, the double summations and whatnot, right? They were quite a pain. But in Calculus 1, we had a theorem that kind of helped us that said that, well, instead of doing all these limits of Riemann sums, we can actually just use this thing called the fundamental theorem of calculus, do an antiderivative, and then plug in the endpoints, right? F of B minus F of A sort of deal. And we have kind of a saving theorem here as well, which means that we don't have to do all those limits of Riemann sums. And this is going to be Fubini's theorem. So Fubini's theorem says that if you're interested in evaluating out this double integral, this is actually equivalent to doing iterated integrals. So I'm going to go ahead and set this up. So maybe we have a function f of x, y, and we could integrate first with respect to y, so dy first, and evaluate out this integral and all that sort of stuff, and then integrate with respect to x, and just do one right after the other. And right, you could probably even guess, right, that symbol for the double integral means that it's going to be kind of equivalent to some do one integral, then do another sort of deal. Let's set up our bounds here. It looks like our y bounds would range from c to d, and our x bounds would range from a to b. Well, then you would have to ask, right, is there something special about y that y has to come first? Or could you have it that x comes first? And the answer is, well, yeah, you could have x come first. And so this is also going to be equivalent to an iterated integral, where you first integrate with respect to x, and then you integrate with respect to y. So x bounds would be from a to b, y bounds would be from c to d. As you do more and more of these problems, typically don't write these parentheses, but you do have to know that your inner limits here correspond to your inner, dy versus dx sort of deal. And so this one here, if I wanted to include the parentheses just to really emphasize that, again, my a to b are x values. So they're all on the inside. And then outside of that, right, are all the y values, dy. So again, when we do problems, you're likely to see them like here in example 2.2, where they don't have the parentheses. But if it helps you, right, you can of course write in your own parentheses. But as you do more and more of these, your eyes will adjust and you'll kind of get used to it. All right, well, so like I mentioned here, just as integration and antiderivatives basically became synonymous, so will double integrals and iterated integrals. We'll almost use these interchangeably. So technically, this is the iterated integral here. And the double integral is what we were calculating out in 15.1. But again, because of this theorem, we find that they actually calculate the same thing. They're equal to one another. And so we'll kind of start to abuse the terminology and sometimes say double integral, even though we're calculating out an iterated integral and vice versa. All right, let's see an example, and then I'll open the floor to any questions. So we're going to evaluate out this iterated integral here. So again, the first thing that I'm going to be doing, and we're always going to basically work inside out. So I'm going to include in parentheses this time. Maybe in future ones I won't. But we're going to first integrate with respect to y. So when I integrate this with respect to y, and again, we have to think of x as a constant, some, again, just unknown constant, but constant with respect to y. So when I integrate this, the x squared is going to be along for the ride, just like if this was a 4 or a 9 or a 25 or whatever. And then I integrate y, so I'm going to have 1/2 y squared. And of course, if you want to put your 1/2 out in front, that's perfectly fine too. And then we're going to evaluate this from y equals 1 to y equals 2. After we do all that, we still have an x integral to evaluate. So we're going to do all this, and then we still have to integrate with respect to x. So let's see. I'm going to write 1/2 x squared. And when I plug in my 2 and square it, I'm going to get 4. And when I plug in my 1 and square it, I'm going to get 1. So this is going to be 4 minus 1 there. Now I still have to integrate this with respect to x. So I have a 3 and I have that 1/2. So I'll go ahead and factor out that 3 and that 1/2. But so I'm going to be left with, I have to integrate x squared. So when I integrate x squared, I'm going to have 1/3 x cubed. And again, this is what I need to evaluate from 0 to 3. We can cancel a little bit. So 3 cubed is going to be 27. 0 cubed is going to be 0. And so my final answer at the end of the day is going to be 27/2. Any questions about Fubini's theorem or this first example, anything we've done so far? All right. Well then, I have a little bit of a remark here, right? The main way to make these double integrals more difficult, at least as of right now, when we're just integrating over rectangles, is to make the integration itself more difficult. So tests more, you remember Calc 2 sort of stuff, which is sometimes okay for the homework, but isn't much for the quizzes and the exams. So I'd say for the quizzes and the exams, quite often we max out at U sub, right? That was an integration technique. We've seen that already a number of times here. On the homework and whatnot, we'll also typically include some integration by parts. Maybe I'll try to do an example of that today. Integration by parts, again, is a very important integration technique of the lot that you learn in Calculus 2, which was, partial fractions and trigonometric substitution. Integration by parts was, of course, down there. Right? Integration by parts is the most important, and it gets used a lot in Calculus 4. And so more than anything, we just don't want you to forget about this if you have to go into Calculus 4, because then it comes up quite a lot. So it's good to have a few here and there, again, on homework problems and things like this, just that way you don't lose those skills, before you reach Calculus 4 or DiffyQ. All right, any questions? All right, well, let's go ahead and try another one then. So actually, this is maybe a good one I'll let you give a go at. So please take 90 seconds or 2 minutes or so. Now we have a double integral rather than an iterated integral, right? And we have, it's bounded by this rectangle, x equals 1, x equals 3, y equals 0, and y equals 1. Another 30 seconds or so, just as far as you can. All right, let's start talking about this one together here. So this one, it didn't specify an order of integration. And so you really can choose either one, right? That's the power of Fubini's theorem. It says that you can either integrate with respect to y first or with respect to x first. I've started to write out the work if I was to integrate with respect to y first. But again, if you want to do the other way, we should all get the same answer at the end of the day. So working inside out, I'm first going to integrate with respect to y. So y to the 1/2 becomes y to the 3/2. But then, of course, you need that 2/3 in front to make sure that you get the right antiderivative. Again, if you were to take the derivative of this, you should get back to where you started. Then we can plug in. And one of the most common mistakes that I see, especially, again, on like quizzes and exams when there's a countdown timer and all that sort of stuff, and folks can get a little bit flustered, is that sometimes I see people plug in that 0 and that 1 for x's accidentally. But again, those are y values, right? So we should only plug them in for y's, and we still have to do all the x stuff later on. So that's just one thing to kind of watch out for, is make sure that you're very intentional about plugging in your bounds and for which variables and whatnot. In fact, I've even seen some textbooks, our textbook doesn't do this, but they specify the bounds like, as x or y values. So you may see like y equals 1, y equals 0, x equals 1, x equals 3, like actually up there in the bounds. So this is, legitimate notation and all that sort of stuff. And again, it just really emphasizes that the 0 and the 1 are y bounds, and the 1 and the 3 are x bounds. So if that helps you, by all means, you can certainly do that. All right, let's go ahead and evaluate. Last bit here, 2/3 still along for the ride. When I integrate x to the -2, I need to raise my power by 1 and then multiply by the reciprocal of that new power. Again, you can double check. If I take the derivative of this, I should get back to where I started. And then I need to evaluate that from 1 to 3. Now, when I'm doing calculus and whatnot, I find that having the negative exponents is fine and all, but when I personally do more algebra or evaluation here, I personally like to write this as 1 over x, right, instead of x to the negative first power. So now when I evaluate, first plugging in 3 and then plugging in 1, right, instead of 3 for x, look like 1/3, and then I'm supposed to subtract away instead of 1, right, instead of x, I'm going to plug in 1. So this ends up being -2/3 times -2/3. So I get an answer of +4/9 at the end of the day. So that right there would be my final result. Any questions on this problem here? So again, some of the intermediate steps may be slightly different for if you were to do it the other way, integrating x first and then y, but you should still get the same answer out at the end, right? 4/9. An interesting thing that I want to bring up, which as of right now, it doesn't seem all that useful, but later on in 15.8 and 15.9, when we have triple integrals, especially in cylindrical and spherical, this gets used quite a lot. And so it's a worthwhile kind of skill to know, and when you can apply it and when you can't. So the two problems that I've shown you so far, if you were to naively kind of completely separate these things, right, and just integrate all of the x's together, just integrate all of the y's together, and then multiply those results, you get the exact same answers, 27/2 and 4/9. And so the question becomes, does that always happen, right? Can you always separate integrals out like that? And in which case, why are we doing it this more complicated way? This seems nicer, right? And the answer is sadly no. So sadly, this cannot always be true. However, In some nice cases, the answer is yes, it will work. And so I need to tell you what that nice case is. And it's essentially that you have a function that you can break up and you have just all of your x's together multiplied by all of your y's together. So you need to be able to write your function just a function of x's times a function of y's. Then in that case, if you were to go and try to evaluate out the integral, and again, you need constant bounds, which in our section here, we're always having constant bounds, so that's nice. Then you can go ahead and split up that integral into just your x integral times just your y integral. And if you do that in this section here today, this will save you maybe 1 line, 2 lines if you're lucky, sort of deal, right? It's not a huge time savings. However, like I said, in 15.8 and 15.9, when we're doing triple integrals, and especially in cylindrical and spherical, this trick right here can save you like 3 or 4 lines. And so although right now it's not, super useful, it'll become much more useful later on. And so it's kind of a fine thing to learn about now. I do want to mention though, that again, this does not work for every function out there. You can have functions as simple as f of xy equals just x plus y. If you have this function here, x plus y, there is no way, no matter how clever or hard you try, that you can write this as a function of just x's times a function of just y's. This doesn't work with addition or anything, by the way. It only works with multiplication. And so even if you said, well, I'm going to factor out an x then, right? Then you're going to have 1 plus y divided by x. So again, you don't have all of your x's together times a function of just y's. No matter what you do, kind of this function, right, doesn't set itself up well to use this trick on. And so this trick is nice when it works, but it's not always going to work for us. All right. Any questions about this? All right. Well, now I'd like to talk through a longer example. Like I said, if you want to make the problems more difficult, right, you can introduce harder integration techniques essentially. But like Calc 3 wise, conceptually, they're no more difficult. It's just that kind of the integration techniques are more difficult. So I've written this one up ahead of time. I'd like to kind of talk through this and give you a chance to ask questions. And I did want to emphasize this has another way that we can specify the bounds here. So far, the bounds have been given to us either as, well, they're just a part of the problem, as in they're already in the statement here. We've also had it where they're listed out very nicely, bounded by x equals 1, x equals 3, y equals 0, y equals 1. Very clear to see what the bounds are. This one, I've given another example of how you can specify the bounds, but it's maybe the most complicated one that we've seen so far. And it relies on us knowing a bit of algebra here in order to decipher this. And so I want to remind you of an old algebra theorem that we had about absolute value inequalities. So for absolute value inequalities, if you have the absolute value of some expression, and it can be quite a complicated expression if you'd like, just any old expression here can have x's and y's in it or what have you. If this is less than or equal to some constant, that this is equivalent to a compound inequality, right? So absolute value inequalities are equivalent to compound inequalities. Either, and you need the expression A to be less than or equal to k, but you also need it to be greater than or equal to negative k. So these are equivalent to each other. The reason why absolute value inequalities are used is because these are actually quite useful for like distance and whatnot, not only in 1 dimension, but in 2 dimensions and higher sort of deal. So that's kind of why, even though it's a bit more complicated, mathematicians still use these quite a lot. So let me go ahead and rewrite this then. So here we have our complicated expression A, less than or equal to some constant. So that means that our expression needs to be less than or equal to pi over 2, but it also needs to be greater than or equal to negative pi over 2. And if I want to figure out what my bounds for x should be, well, then I'm just going to use rules for compound inequalities, and I'm going to add pi over 2 to all sides. And essentially what I'm trying to do is just isolate x in the middle here. So by adding pi over 2 to all sides, notice I cancel out this negative pi over 2 here. So that's really my motivation why I would do such a thing. So on the left-hand side, that means I would have 0. The middle, again, I'm just going to have x. And then on the right-hand side, pi over 2 plus pi over 2 is going to be pi. So this tells me that this absolute value inequality is equivalent to having x range between 0 and pi. Let's go ahead and do this other one here as well. So y minus pi should be less than or equal to pi over 2, and it should be greater than or equal to negative pi over 2. So again, using that old algebra theorem, and rewrite here. So if I add pi to all sides, pi over 2 plus pi would be 3 pi over 2. And negative pi over 2 plus pi is going to be positive pi over 2. So this just tells me that this is equivalent to the bounds y ranging between pi over 2 to 3 pi over 2. Right? And of course, this will be our lower bound, the pi over 2, and our upper bound will be the 3 pi over 2. So, okay, absolute value inequality, quick refresher. Okay, so this problem here would like us to evaluate out this double integral. So again, you can choose either integration first. You could integrate with respect to y first or with respect to x first. Because, right, when I'm looking at this, I see that, you know, if I'm thinking about holding one of these things constant and integrating with respect to the other one, I kind of have to think about, you know, if x was constant, you know, I'm thinking that this is going to be like integrating, you know, maybe there's a 2 out here or something like this, but essentially sine of y. And I think that sounds quite nice. That's all right. But if I was to hold y constant and integrate with respect to x, you know, I have this x outside as well. So then I'm going to have like x sine x. So when I'm trying to decide, should I integrate with respect to y first or should I integrate with respect to x first? Really, it's a question about maximizing partial credit. And I want to integrate the easier one first to make sure that I actually show some work and whatnot. And then if there's a harder one, saving that for second's not so bad. To integrate x sine x, does anyone remember how to do such a thing? This is something maybe from calculus 2. Yeah? So tabular integration is a fancy long form version essentially of integration by parts, right? So yeah, tabular integration is fine, but since you're only doing it once, integration by parts is probably, I don't know, hair quicker or whatnot. But if you needed to apply integration by parts multiple times, 2 or 3 times, definitely tabular is the way to go. All right, so yeah, if you want to integrate x sine x, you have to use integration by parts. So that's why just integrating a constant, you know, 2 sine y or something like this is much easier. So with that, I've justified, I hope, maybe why I would integrate with respect to y first. So notice my setup here. The y bounds range from pi over 2 to 3 pi over 2. That's what we had. And the x ranges from 0 to pi, right? So that's, again, those absolute value inequalities set up our bounds here. If I integrate this with respect to y, again, my x is constant here. There's a small little u substitution, but you can almost do like a guess and check here. By integrating sine, I'm going to get negative cosine. And then again, x is constant with respect to y. So the derivative of the inside is just going to be 1. Right? And so, of course, you can double check. If you take the derivative of this, partial derivative with respect to y, you do get back to where you started. Now we can plug in our bounds. Again, these are y bounds. Y equals 3 pi over 2, and y equals pi over 2, and subtract. So once I've done that, we can see that I have a couple things that are going to require integration by parts. Now you can evaluate this out just as it is, and that's perfectly fine. But there is a little bit of a trick if you want to use it, right? Some good old trig identity rules here that allows us to switch, right? Cosines and sines are basically just shifted versions of one another. Right? If you just shift sine by enough or shift cosine by enough, right, you get the others. And so, for instance, if you were to shift cosine by 3 pi over 2, right to the left, you actually get the same sine function. So this right here is an old trig identity. I guess you could also use the angle addition formula in order to prove that as well, but that's a little bit of overkill. And likewise, cosine of x plus pi over 2. If you just kind of shift that to the right by pi over 2, you get negative sine. So again, completely optional, but if you do decide to take advantage of this, you get down to just needing to evaluate out this integral x sine x from 0 to pi. And there's a constant out in front. So now we've simplified it, right? We don't have to use integration by parts twice, but we still have to use integration by parts once. Can't get away from it. So the integration by parts, we need to select a u and a dv, and then calculate out du and v. So I don't know, you like ILATE or LIAT for integration by parts orders here? Which one have you heard of before? Lipit? What is Lipit? I'm going to learn something new.
Polynomial exponents trig.
Oh, wow. Logs, inverse, trig, I assume. Polynomials, exponentials, and trig. So I guess the only thing that you would have to make sure that you agree with is that when you have something like square root of x, that's not really a polynomial, but it would kind of live in the same sort of realm as the polynomial level sort of deal. These are all kind of, as you work your way down, these are good choices for u, and as you work your way up, these are good choices for dv. So you usually take the highest thing on the list and make that your u, and you take the lowest thing on the list and you make that your dv. So in this case, we have a polynomial, x to the first power, and we have a sine of x. So polynomial, and we have a trig. So the highest on the list, that's going to be our u. The lowest on the list is going to be our dv. And that works, I would say, 95% of the time. All right. So we calculate out these others, and then we can go ahead and plug in, use the integration by parts. And at the end of the day, we get negative 2 pi. So after all is said and done, the answer is negative 2 pi. Like I said, though, like Calc 3 wise, nothing was more difficult about this, conceptually Calc 3 wise. However, the Calc 2 was killer on this, right? So does this really belong in a Calc 3 test or final or quiz or something like this? Not so much, right? So it's good that you remember integration by parts, but this is kind of overkill for testing your Calc 3 knowledge. All right, that being said, let me pause here. I covered a lot. Any questions about any of this that you'd like to discuss before looking at another one? Okay. So then, here's one that's a bit kinder. Maybe we can do this one together. Find the volume of a solid enclosed by the surface, z equals x secant squared y, the planes, z equals 0, x equals 0, x equals 2, y equals 0, and y equals pi over 4. When we're sitting here in a class about 15.2, it's obvious what to do, right? You need to integrate something. We're in a class or a section that's about double integrals. So your mind kind of goes very quickly to, I need to use a double integral here. It's considerably more difficult, I would say, like on the final exam, when we've had an entire semester's worth of content, right? And you need to decide what to do. Should I be taking partial derivatives of this thing? Should I be integrating this thing, right? How do I solve this? And the key word here is going to be volume. So as we learned in 15.1, that volume is going to be the double integral, especially of a nice positive function here, over some region. So whenever you want to calculate out volume, a double integral is a good way to go. And this is always the volume kind of above the xy plane, or AKA z equals 0. So if you had two interesting surfaces, right, then we would need to do something else. In fact, we'll develop triple integrals, and they will also be good at finding volumes. But for the time being, right, This is finding the volume between some interesting surface and the xy plane, aka z equals 0. So all this is the setup for, hey, we're going to integrate x secant squared y. We're not going to use a limit of a Riemann sum, right? We're going to use Fubini's theorem and integrate this either with respect to y first or with respect to x first. Kind of my default is always just do dy dx, do y first, unless if there's a compelling reason why you should use x first. So that's just kind of my default. And in this case, right, if you looked at this and you say, I really don't know how to integrate the y, but I know how to integrate the x, right? Then you could go ahead and do the x integral first, right? But if you know how to integrate both of these, right, well then either one's fine. And then all this other stuff are bounds, right? So we have x equals 0 and x equals 2. We have y equals 0 and y equals pi over 4. Now this is one of these that we do have a function of just x's times a function of just y's, and we have all constants in our bounds. So this is one of them that if you wanted to, you could go ahead and split this up and integrate all of your x stuff, integrate all of your y stuff, and then just multiply those results together. So if you want to get a little bit of practice using that trick, again, it is a theorem, it's a proof, but again, it doesn't work on every single problem or anything, then you could go ahead and split this up. So integrating the first one with respect to x, we're going to have 1/2 x squared. I need to evaluate that from 0 to 2. Next up, integrating secant squared. What's the answer? Integrating secant squared, what is that? Tangent, right? So a bit of calculus 1 here, just a reminder. It's a handful of things that you need to have memorized, right? Just like the integral of cosine is sine and things like this. The integral of secant squared being tangent is one of those. So we're going to have 1/2, 2 squared is 4, 0 squared is 0. Then we're going to multiply that by tangent of pi over 4 minus tangent of 0. And we get a calculator in this class, so right, make sure your calculator is set to radians mode. But if you plug these things in, it'll tell you that tangent of pi over 4 is 1, and it'll tell you that the tangent of 0 is 0. So ultimately, this is going to be 2 times 1 minus 0. We get an answer of 2. Questions on this one? Okay. Another thing that we could throw at you, right? So this one asks you to find a volume. Another fair game question would be find the average value, right? So find the average value of this function here, rectangle with vertices 0, 0, 4, 0, 0, 1, and 4, 1. So we could sketch this out. 1, 2, 3, 4, 1. So 0, 0, 4, 0, 0, 1, and 4, 1. You don't have to sketch this out, all right? I just want to justify what my bounds are going to be here. So average value, again, this was something that came up in 15.1. We're in a section that's all about double integrals. So you're probably thinking, well, I need to have a double integral, right? Yes, of course. So we are going to have a double integral. We're going to integrate e to the y root x plus e to the y. And again, I'll start with dy dx, and I may switch that here in just a second. My bounds, well, this goes from x equals 0 to x equals 4. And we have y equals 0 to y equals 1. If I just was to evaluate it out like this, I would get the wrong answer, though. There was something extra that you needed for average values. Anyone happen to remember, for average values, what's the extra thing that you need, yeah? Yeah, exactly. So it's 1 over the area of the region that you're integrating over. So in this case, we are integrating over a 1x4 rectangle. So the area of a 1x4 rectangle is going to be 4, right? It's just length times width. And so in order to get the average value, we're going to have this 1/4 out in front. Otherwise, we're calculating out volume, right? But this is going to be the average height. All right, so this right here is my setup. And again, this one we could go ahead and integrate with respect to X first. The integration with respect to Y, though, isn't super daunting, just because I noticed here that if you let U be equal to X plus e to the Y, this inside stuff, then du is going to be equal to, and again, I'm taking a derivative with respect to Y here, so it's going to be e to the Y dy. So notice that all of this stuff on the outside here is essentially just a du. This is another one of these, by the way, that no matter how hard you try, there's no way to get a function of just x's times a function of just y's. They're too intertwined with one another. The square root kind of ruins things, right? And so there's no way to get all of your x's times all of your y's. And so using that trick, like we did back here, where you could separate out the integrals, isn't going to work on this one. So, okay, I'll integrate with respect to y first and do this u substitution. So again, I have this 1/4 here. We're going to have to do all of our x's here in just a second. But if I integrate essentially square root of u, this is going to become u to the 3/2 times 2/3. And u was this function of x plus e to the y. So double check, if you took the derivative of this with respect to y, the 3/2 would come down and cancel with the 2/3, leave the inside alone. Reduce your power by 1, so instead of 3/2, you'd get 1/2, and that would give you exactly this bit right here. Then you need to multiply by the derivative of the inside, again, with respect to y. When you take the derivative of the inside, e to the y there, right, you get this extra piece. So yes, you do get exactly back to where you started. So this is the correct antiderivative. We still need to plug in y's ranging from 0 to 1. Let's go ahead and bring out my other constant here. I have this 2/3. So if I'll leave it in this line. But if I was to bring this out, right, there's a little bit of cancellation. I think we're going to get what, 1/6 when we combine it with the 1/4 there. All right. When I plug in y equals 1, I get x plus e to the 3/2 minus when I plug in 0 for y, I get x plus 1 to the 3/2. All right, well, one more integral to go, but this isn't so bad. The x integral you probably already suspected was going to be easier. So if I integrate x plus e, and again, e is constant, just like 2.718 and change sort of deal. But when I integrate this, I need to raise my power by 1, multiply by my new reciprocal out here, 2/5. Double check, if you take the derivative of this, you should get back to where you started. Minus x plus 1, again, raise that power, put a 2/5 out in front. And this I need to evaluate from 0 to 4. There's a 2/5 on both of these. I'm going to go ahead and factor that out and combine it with my 1/6 a little bit here. So I think I'm going to get what, 1/15. Let's go ahead and evaluate the rest of it. So let's see, I'm going to have what, 4 plus e raised to the 5/2 minus 0 plus e raised to the 5/2. So that's me just taking care of this first bit here, plugging in first 4 and then 0 and subtracting the results. And then I need to subtract away. And now let's work on my second term. When I plug in 4 into this, I'm going to have 5 raised to the 5/2. And I need to subtract away when I plug in 0, I'm going to have 1 raised to the 5/2. So we can distribute that negative, for instance, here to each piece and do a little bit of cleanup, but this is probably a good place to end for this one. So wouldn't be the funnest one that I've ever plugged into my calculator or what have you, or typed into WebWork, but not the worst either. So this one, a little bit more challenging than the last one, certainly. It required a U substitution, but this is where I'm really hoping that this is a good problem to, or like a good level to get to, especially by the time you get all of your WebWork homeworks done. So I hope you'll be able to do problems like this in a fairly timely manner. Again, the only thing that was required for this one was U substitution. All right, any questions on this one? All right, well, the last bit here, we were not going to spend much time. I will let you guys out a little bit earlier, but once upon a time, a student asked me, this was a textbook problem, and asked me how to do this. And it turned out to be a lot harder than I thought at first glance. And so I had written this up for the student, and so I thought I would include it here. So this was the problem. You can see that there's going to be a little bit of integration by parts and maybe some trigonometric substitution in here. So yes, like x over x squared plus 1 is the U substitution, so that's going to be a little bit easier. We go ahead and integrate that, so get rid of all of our x's. Turns out that you need some integration by parts at that point. The problem after all of this is that you get indeterminate forms. So you're really back in calculus 2. When you start trying to plug in your bounds, it turns out these were some improper integrals. And so when you plug these things in, you get 0 over zeros and stuff like this. And so you have to use L'Hopital's rule on it. So once you use L'Hopital's rule and everything, you get an answer at the end of the day. But again, huge mess. So anyway, again, just showcasing that the problems can be harder, but it's really not calculus 3 that's doing making them hard. It's really the calculus 2. And so something like this wouldn't be appropriate, right, for quizzes and exams. So anyway, I'll stick around if there are any one-on-one questions. Otherwise, again, make sure you go to recitation tomorrow, get back your midterm. And Friday's class, we're going to make this harder in a calculus 3 sense. And instead of integrating over rectangles, we'll do more general regions. So that'll be the topic for 15.3. All right, have a great day.